My name's Lisa. I'm going to be a first year PhD student at UC Berkeley, and today I'm really excited to talk to you all about RubberBand, the cloud-based system for hyperparameter tuning. So, cloud computing is huge, and machine learning developers have been moving a lot of their ML workflows onto the big cloud providers, and a lot of the operational costs of these machine learning companies are going to cloud compute. So the question is, because compute is so expensive on these providers, why are we still doing really computationally expensive procedures like hyperparameter tuning in the same way that we would in a data center environment where we have a fixed pool of resources and we frankly don't care as much whether we're underutilizing them? So what is hyperparameter tuning and why are we doing it incorrectly? Well, hyperparameter tuning aims to determine the optimal configuration of model hyperparameters by repeatedly training different candidate configurations or trials and selecting the one which yields the highest accuracy. So there are many different ways in which you can go about doing this hyperparameter tuning. We're specifically going to focus on what are called early stopping techniques, in which you launch a ton of trials and you eliminate them in stages. So we're going to focus on what's called the successive halving algorithm, which simply halves the number of trials for each stage, eliminating the ones with low accuracy. So these techniques tend to exploit stage level parallelism, which reduces overall job completion time by running training and evaluation concurrently for all trials within that stage. However, these techniques thus far have only focused on exploiting parallelism over a fixed pool of compute resources. So why can this be a problem in the cloud setting? Well, when you're running this all on a fixed pool of resources, this can lead to a degradation in cluster resource utilization throughout the experiment as the numbers of trials decrease. So either you can have the number of resources per trial or the trial level parallelism stay the same throughout the entire experiment, in which you're going to leave a lot of resources idle for a lot of the experiment, or you can increase the trial parallelism as the poor performing trials are eliminated, which is a better option, but leads to significant communication overheads, and thus the model throughput will actually scale sublinearly with the number of machines that you give it. So either way that you do this, you are effectively wasting resources when you run these early stopping algorithms with a fixed pool of resources. So this may not have been a problem in your traditional data center, but when you're running on the cloud, where say training BERT takes $7,000, this can quickly lead to wasting so much money. The most cost-effective solution here would be to simply run each trial with one resource for the entire duration of your experiment, deprovisioning instances as they are no longer needed. So while this is quite cost effective, it is not time effective, as most times your duration of your experiment will be quite long. So many machine learning developers are willing to sort of trade off the efficiency that comes from not scaling your model in order to get a shorter job completion time, which is where this problem gets so interesting. So what we're trying to solve is, given a time constraint, how can we minimize the execution cost of a hyperparameter tuning job? In order to solve this problem of efficiently leveraging elastic cloud resources for hyperparameter tuning, we break it down into three key challenges. The first is how to accurately model the job completion time and cost of a job on the cloud as a function of a resource allocation plan. This would need to incorporate both model performance metrics such as training latency and scalability, along with the cloud provider metrics such as cloud provider overheads, the billing model, and the price of each resource, as well as any data movement fees. The second is how to navigate the large search space of plans to find a feasible low-cost solution. that completes within a given deadline. And the third is how to efficiently schedule and place workers of this low-cost allocation plan over an elastically provisioned cluster at runtime, specifically so that we can optimize for worker co-location and maximize cluster utilization. To address these challenges, we designed RubberBand, the first framework for cost-efficient, elastic execution of hyperparameter tuning jobs on the cloud. For each of the above challenges, we make the following contributions. First, we develop a cost and latency model that synthesizes profiling information about the input job and target cloud resources to evaluate the benefit of running hyperparameter tuning jobs over elastic resources. Second, we design and implement a DAG-based execution model that finds a cost-minimizing resource allocation plan for the time-constrained hyperparameter tuning workload. And third, we build a full stack system for hyperparameter tuning on the cloud, which generates and executes an optimal placement plan to maximize worker co-location and cluster utilization. Next, we will go into each of these three components and how they work. First, let's look at how we solve issue number 1, modeling job completion time and cost of a given allocation plan for a given hyperparameter tuning job. In order to solve this problem, we're going to need two things: the data pertaining to the performance and cost of your job, and the simulator to utilize that data to determine the overall performance and cost. We're also going to need to take into account any potential fluctuation in training latency, as that could end up with stragglers at the end of a stage. So to obtain the data pertaining to performance and costs, RubberBand is going to run a profiling step for a configurable period of time prior to execution in order to collect the data associated with model training and resource management. So this process involves iteratively scaling up and down resource allocations by powers of 2 and measuring the training latencies for each allocation, usually taking on the orders of minutes to complete. So once this data is collected, it's used to simulate the latency and cost of executing a candidate resource allocation plan. So how do we simulate this? Well, for each potential allocation plan, RubberBand simulates a DAG that incorporates the cost and latency of initializing an instance, scaling up or down, training the models for a specific number of epochs with a specific number of resources, and evaluating the model accuracy at the end of each stage. So on the right here, we've shown an example of how this would look when you give it a successive halving experiment with 3 different stages. Here, the red nodes indicate that a stage has ended and you need to sync back up to determine which trials get to continue on to the next stage. So to account for potential stragglers here, we sample the training latencies for each node type from a distribution which we parameterize by the profiling data that we have. So once this DAG is generated, the planner can predict job completion time of a candidate allocation plan by computing the critical path in this DAG. Cost can also be calculated in a similar manner with differing methods based on your billing model, whether it is per function or per. Now that we've figured out how to best model the performance and cost of a given allocation, we need to move on to issue number 2, finding an allocation plan that minimizes the cost while completing before your given deadline. RubberBand's resource allocation planner is responsible for generating this feasible resource allocation plan that minimizes the predicted execution cost. To do so, this planner is going to start with a feasible solution, which means a solution which is able to complete before your given deadline. And then this plan is iteratively improved upon in a greedy fashion with the following 4 steps. First, we're going to take the current best allocation plan and we're going to generate a new set of candidates from it by iteratively decreasing the number of resources for each stage. Second, we're going to predict the job completion time and cost of each of these candidate plans with RubberBand Simulator. Third, we're going to greedily select the best candidate. And fourth, we're going to iterate again with the new best candidate as the best configuration. So the way that we predict what the new best candidate is by maximizing what we call the cost marginal benefit, which is the reduction in cost normalized by the increase in runtime. So intuitively, we want a plan that is able to reduce costs without significantly increasing our job completion time. Now that we have both our simulator and our low-cost allocation plan, we can move on to issue 3, how to effectively execute this allocation plan in a way that optimizes for worker co-location and maximizes cluster utilization. So this is done by RubberBand's executor, which is comprised of a scheduler, a cluster manager, and a placement controller. So at the end of a stage, or whenever a cluster needs to be changed or resources need to be reallocated, the scheduler will request the cluster manager to provision new nodes or to deprovision existing ones. And then to relocate workers, the placement controller will convert the resource quantity allocated to each trial into physical resource assignments for its workers. So what this placement controller is going to do is it's going to place parallel workers of a trial onto a single machine, or at least packed into a minimal set of nodes. Why do we want this? Well, by co-locating workers, the distributed training algorithm will avoid incurring any unnecessary network overhead. So here we've depicted the system architecture of RubberBand. It's built on top of Ray, which is a distributed computing platform. Pink arrows are going to represent invocations, while gray arrows are going to represent object dependencies. So like we talked about, the profiler and the simulator are going to be the ones which model job completion time and cost of a given allocation plan. This simulator is used by the planner, which generates candidate plans and finds the one that is low cost. And then this low-cost allocation plan is fed into your executor, where your scheduler is going to schedule the trials, determine which ones get to continue. Your cluster manager is going to control the cluster, make sure it's the right size, and your placement controller is going to make sure that your trials are placed in a way which maximize worker co-location and cluster utilization. So now that we've gone through how RubberBand works, let's look at what everyone's interested in, the end-to-end results. So for these end-to-end results, let's first check to make sure that the simulation that we have described in RubberBand is able to accurately predict the job completion time and cost in a real-world setting. So the above graphs here show the simulated predictions of the job completion time in seconds and the cost in dollars when running a 20-minute experiment training ResNet 101 on CFAR10. And then the orange bars represent the real job completion time and cost when running the same workload on an AWS P3 8x large instance. So here we can see that the simulation is highly accurate to what we see in real time. So now that we know that the simulation is accurate, let's check what the actual cost savings are. So here we are running again on AWS P3 8x instances, and we're showing the difference between running on a static cluster and RubberBand on 3 different data sets with 3 different models. So first we have CFAR10 on ResNet 101, CFAR 100 on ResNet 152, and RTE, which is part of the GLUE dataset benchmark, which is for NLP, and this is on BERT. So we can see that RubberBand is able to reduce the cost by 20 to 53% in all of these instances. So to better understand the exact cost benefit of RubberBand in your different hyperparameter tuning jobs, we run the same successive halving experiment for ResNet 101 on CFAR10 with 3 different deadlines. So as we can see here, as the deadline increases, the cost savings of RubberBand decreases in relation to the static plan. So why is this? Well, this is simply because the number of resources per trial in the static method goes down the longer your deadline is, because you don't need to stack resources on a single trial to make it run faster. And so this is going to get closer and closer to the most cost-effective plan, which is to simply run one model on one GPU for the entire duration of the experiment. Well, that's all the time I have for right now. But if you would like to see some more experiments, specifically ablations on the effect of our placement policy or the effect of the different aspects of your profiling information, like your instance latency, your training latency, or anything like that, please come check out our paper. I'm happy to take any questions, and thank you so much.